Okay. So let us start this particular session. So in our previous session, we have started with the number systems in digital design. Now, so let me share my screen also, and please let me know whether my screen is visible or not. 1 minute. Yeah. Please confirm me whether my screen is visible. Yes. 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 1 minute. Yes. Okay. Let us start this session. Let me share the PPT. Yes, I think my screen is visible. Yeah. So this is day four of digital design workshop. And so before starting our session, first let us briefly discuss about our training program, which is going to start from 3rd Feb 2025. So it is a VLSA RTL design and verification. Both offline course and online courses are going to start from 3rd Feb 2025, and you are going to get 20% performance job guarantee and job assistance for remaining 80% candidates who have registered for this particular paid course. And we have guarantee internship opportunities in our own company. And these are the contact details you can contact if you are interested in our particular offline and online courses. This is about VLSA design and verification course. We have other courses also, like physical design, everything we have. Okay. Yeah. So let us start the session. 1 minute, 1 minute. Give me 1 minute time. Yeah. 1 minute. Yes, 1 minute. I will show. Okay. You can contact these numbers, and you can just simply inquire about the courses. So we have physical design, analog design, okay, and VLSA RTL design and verification. Okay. So both online and offline. You can just inquire them. Okay. So shall we start the session? Are you ready? Everyone is ready? Day four. Okay. Shall we start? Yes. 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 Now. So let's see some binary coded decimal. We'll see some number codes. So we have different type of codes in this. So let's see. Let's start with binary coded decimal, or you can say 8421 code. So coming to this binary coded decimal BCD, which is a type of binary code used to represent a given decimal number in an equivalent binary form. And the BCD equivalent of a decimal number is written by replacing each decimal digit in the integer and fractional parts with its 4-bit binary. Okay, it is represented in 4-bit binary. So let's say if we have a decimal number 0, so what is the BCD code for that particular decimal number? It is 0000. You can follow 8421 for writing the BCD equivalent of this particular decimal number. This is your decimal number on the left hand side, and on the right hand side you have BCD equivalent. Okay, so for one, what is it? 0001, and for two it is 0010, and so on. We have the BCD representations only up to 9. Okay, that is nothing but 1001. Okay, so here the BCD codes can be written up to only 9. Okay, up to the decimal number 9 we can write the BCD equivalents. Okay, Let's say if we have a decimal number, let's say 12. Okay, so if we have a decimal number 12, and if we want to represent this particular decimal number in BCD, then how we are going to represent it? We should represent it individually. So every individual digit has 4-bit binary BCD representation. That is, 1 is nothing but 0001, and 2 is nothing but 0010. So this is the BCD representation of this particular 1, 2. Is it clear? We have many like 5421, and why we are using 8421. Yes, we can use anything. 5211 also you can use. No issue. 8421 is mostly used. Okay. Yes. I am telling this is 1 2. For this 1 2 we will get. But let's say uh, after this 9, okay, so after this 9, that is for 10, for the whole number 10 we don't have any BCD representation. For whole number 11 we don't have any representation, BCD representation. So from 10 to 15, for the whole particular number we don't have any BCD representations. Is it clear for everyone? So if we want to represent any number 15 greater than 9, that is 10, 11, 12, then we should represent each digit. We should write the each digit BCD equivalent, and we should write it. Okay. For whole number, we don't have the BCD representation. So we have BCD representations up to 0 to 9. So is it clear for everyone? Yes or no? If it is clear, please type yes in the chat box. Okay. Yeah. So let's say if we have a number 0010, this is our BCD number, and let's say another number is 1000. So what is the resultant if we add these two BCD numbers? What is the resultant we are getting? 0010 and 1000. 1 minute. 0010 and 1000. What is the resultant we are getting? So answer is 1010. So is this particular BCD code, is this particular BCD code is correct or not? Is this particular BCD code is valid or not? Do we have this particular BCD code 1010? Anyone has the answer yes? Anyone have this particular answer yes? Anyone say this particular BCD code is valid? So BCD codes are from 4 zeros to 1001. So we are getting 1010. Okay. So when we are adding this two particular BCD codes, if we get the BCD representation which is greater than 9, then we are going to add this particular BCD code with 6, 0, 1, 0. Then our answer will be 0, 1 plus 1, 0, 1, 1 plus 1, 0, 1, 1 plus 1, 0, 1. So the carry which we have got in this particular process, this carry we are going to just ignore. Is it clear for everyone? Is this BCD addition clear for everyone? Yes. Yes. So we use this particular BCD codes in our digital watches or 7 segment displays, right? So in that particular cases, we use this particular BCD representation, BCD binary coded decimal representation. Okay. Yeah. Yes. So after 9, we have 10, 11, 12, 13, 14, and 15. So how many invalid digits we have? 6. Okay. So to skip this 6 invalid representations, we are going to add 6. Okay. So then we will get again 0. Is it clear for everyone? Yes. We should ignore the carry. So then only we will get the correct BCD representation, right? So that's why we are ignoring it. Okay. Yes. So is it clear for everyone? If you are clear, then type S in the chat box. Yes. Yes. Next type of code is XS3 code. So the name itself indicates the XS3 code for a decimal number is determined by adding 3 to each decimal digit in a given number and then replacing each digit of newly found decimal number by its 4-bit binary. Okay. So let's say if you want to represent XS3 code for the decimal number 0, so first you can what you can do is you can just simply write the binary equivalent of this BCD equivalent of this 0 0 0 0, and you can add 3 to this 0 1 1. That is nothing but 1 1 0 0. That is 00 1 1. So this is the XS3 code for this particular number 0. Yes, correct. And if we have 2, then what is the XS3 code for this particular? First, you should write it in BCD, that is 0010 plus 0011. That is 1 1101 0101. Yes. Okay. So the XS3 code, is it clear for everyone? Yeah, that is a disadvantage of the BCD. So we can only represent the numbers from 0 to 9. Okay. After 9, we should represent that particular number individually. Every digit should be represented individually. So for representing that particular numbers, let's say if we have to represent 10 in binary, then how many number of bits we need? If we want to represent 10 in binary, how many number of bits we need? Anyone can answer? If we want to represent 10 in binary, my question is if we want to represent number decimal number 10 in binary, yeah, I will repeat. Yeah, how many number of bits we need? 8 or 4? My question is how many number of bits are needed to represent decimal number 10 in binary? In binary, yes, 4. That is 1010. Now, how many bits are required to represent this particular 10 in BCD? 8. Okay. So this is the disadvantage of BCD. Actually, if we use this particular BCD representation, we need more number of bits for representing. If we want to represent 10 in BCD, then we should individually represent it 0001 followed by 0000. This is a BCD representation of digit 10. Is it clear? Is it clear for everyone? Yes? Everyone, is it clear? Yes. Yes. And coming to this BCD addition, we have taken some example, right? Let's say 1000 followed by 0110. Okay, this was our some example. Let's say if we are adding this 111 So is this particular code present in BCD representations? No, right? So this particular BCD representation is not present in BCD codes. So why what we are doing? We are adding plus 60110. So we can skip all the particular 6 representations and we are getting the final answer. 1101, 111 is 101. So we will ignore the carry. So the final answer is 0100. So this is the resultant of BCD addition. So is it clear for everyone? Can we move forward? Yes. Yeah. Now, so coming to this XS3 code, it is determined by adding 3 to each decimal digit and replacing each digit by newly found decimal number by its 4-bit binary. Okay. So let's say for 0 we have 4 zeros and 1 we have 0001 2, 3, 4, 5, 6, 7, 8, and 9. So these are the BCD representations. Okay, 1001. Okay, so if you write the XS3 code for this particular four zeros, then what is XS3 code? It is nothing but 0011. Am I right? 0011. Now, if you take the ones complement of this particular number, so what is the answer we are getting? Double one, double zero. That is nothing but 8 plus 2. Sorry, 8 plus 4, 12. 1 minute. I'm getting one call. 1 minute. Yes. So, what we were discussing, yeah. So this one. So four zeros, which means for this particular XS3 code is 0011. Okay. So if we complement this, what we are getting? 1100. So if we complement this, what we are getting? 1100. Now here the 9. What is the XS3 code for this particular number 9? What is the XS3 code for this particular number 9? 1001 plus 0011. 1101, 1101, 1, 1. This is a number, right? What we are getting? Am I correct? Someone written four ones. How four ones? Yeah. Double one, double zero. So what we are getting here? Double one, double zero. So this number, have you observed anywhere? Double one, double zero. Have you observed anywhere? Where? Double one, double zero. Where we have seen this double one, double zero in the same slide. No, 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 no. Here. So here, four zeros, that means XS3 is 0011. If we complement this particular XS3 code, then what we are getting? 1100. Here, what is the XS3 code for 9? 1100. Can you see this pattern? Can everyone see this particular pattern? Everyone can see this particular pattern? Please confirm me whether can you see this pattern or not. So if we complement XS3 code of 0, then we are getting XS3 code of 9. So if we complement XS3 code of 0, then we are getting XS3 code of 9. That means, okay, so let us, everyone can see this pattern, right? If we complement XS3 code of 0, then we are getting XS3 code of 9. Everyone can see this particular pattern, right? Can anyone cannot see this particular pattern? Yes? Now. So let us take the second number 1. That is 0001. So what is the XS3 code for 0001? 0001 0011 1 1101 11 double one double zero. All of you getting the same code? Double one double zero? 01 double zero. 001 0011 1101 1101 1, sorry, 0100. 0100, right? Everyone getting 0100. The XS3 code for this particular one is 0100. And if you do complement, then what is the answer you're getting? 1011. All of you getting this? Yeah. Now take the XS3 code of 8. So first, what is the binary representation of 8? 1000. So if you take the 1000 and add 0011, that is 11010111. So XS3 code of 8 is, what is the XS3 code of 8? 1011. So the complement of XS3 code of 1 is nothing but the XS3 code of 8. Can everyone see this particular pattern? Can you please confirm me whether you can see this particular pattern? Okay. So here can I conclude that if you want to find the nines complement of a number, then you can simply find the ones complement of x3 code of a number. Can everyone agree with this particular point? If we want to find the nines complement of a particular number, just simply find the ones complement of x3 number. Let's see how we are getting to this particular conclusion. So if we want to find the nines complement of number 0, so how to find the nines complement of number 0? Can anyone tell me how to find the nines complement of number 0? What is the basic procedure of finding complement? How to find the nines complement of a number 0? Yeah, subtract from 9. So what is the nines complement of number 0? What is the nines complement of number 0? All of you please answer. All of you have listened the topic called complements, right? Where we have discussed n's complement and n minus 1's complement. Yeah, subtract from 9. So what is the nines complement of 0? Yeah. What is the nines complement of 0? 9. Okay. Now, the nines complement of 0, how you're finding? You're subtracting 9 from the digit 0. Okay. But what I'm telling is, to find a nines complement of a number, just simply find the ones complement of x3 code of a number. Okay. So how to find the x3 code of 0? Like this we have found, and the complement is nothing but the x3 code of that particular number. So here we have found the complement of this particular x3 code 0, that is nothing but 1100, which is nothing but the x3 code of 9. So everyone got this particular point? Everyone got a clear picture of this particular concept? If it is yes, please type yes in the chat box. So this particular concept is known as self-complementing. So XS3 code is a self-complementary code. Once again, should I repeat? Okay. So what I'm telling is, simply first find the XS3 code of number 0. Okay. That is nothing but 0011. Then find the ones complement of this particular XS3 code. That is nothing but 1100. Now come to the last number 9. Okay. The binary representation of this 9 is 1001. Find the x3 code of this 9, that is 1100. So this 1100 you are getting here when you are doing the ones complement of this x3 code. X3 code. So how to find the nines complement of a particular number? You will subtract 9 from that particular digit. Okay, 9 minus 0, you will get the nines complement of a particular number. What I am telling is, you just find the complement of that particular x3 code. Then you will get the x3 code of that particular number. That is nines complement in a x3 format. That's it. Everyone clear? Is it clear for everyone? So what is your assignment is, fill up this particular table. You find the x3 code of 1, find the complement of that, find the x3 code of 8. Okay. 0 and 9 are connected, 1 and 7, 2 and 6, 3 and 5, and this one will be remaining. Okay. So it is a self-complementary codes. So is it clear for everyone? Is this particular concept is clear? So can anyone tell me what is the advantage of this particular process? Now we will talk in the terms of hardware. So what may be the advantage of this particular concept? Okay. So what may be the advantages in terms of hardware? We will talk as a VLSI engineers. We will talk as a VLSI design engineers. So what may be our okay, reduce complexity. Okay. So what do you think? Subtracting is easy or flipping the bits is easy? What do you think? In your reason, in your opinion, what do you think? Subtraction is easy or flipping the bits is easy? Yes, because subtraction needs more circuitry, whereas flipping the bits just needs some NOT gates. That's it. Okay. So that's why we are going to in particular cases, if we want to find this nines complement, then we are going to use this particular concept of XS3 codes. Okay. Yeah. So is it clear for everyone? Shall we move forward? I think discussed more about this. Okay, no issue. Now, coming to this particular gray code, which is mostly used when we are encoding or encoding purposes, when we are sending the data in our channel. So particularly this gray code is a 4-bit numeric code. It is a unit distance code because successive code words in this particular code in 1 bit position only, and it is also a reflective code that is both reflective and unit distance. So let us see the key characteristics. In the gray code, consecutive numbers differ only by 1 bit. This minimizes the chance of error during the state transitions. And unlike the binary or BCD codes, gray codes do not have any positional weights. So let's say this is our binary code. So what is the value of this particular binary code? Yes. Why gray code is used in KMap? Yeah, this also we are going to see now. Okay. Okay. But if you consider a gray code 1010, let's say this is our gray code, this do not have any value. This do not have any positional value. Okay. Unlike our BCD codes and binary codes, gray codes do not have any positional values. You cannot simply tell it is number 10. If it is representing, if it is represented in gray code, you cannot simply tell it is number 10. Okay. So that is gray codes do not have any positional values. Okay. First, let us see the binary to gray code conversion and gray code to binary conversion. Then we will come to the applications. Okay. Now, so let's say this is our binary number 10110. So how to convert this particular binary number into gray code? The first digit will be copied as it is. Then from the next digit, this particular digit is given as a result of XOR operation of this and this two successive digits. Like this, the successive digits will be XORed operation and it will be converted into gray code. Let's say if we have 0100, this is our binary code. Then what is the gray code of this? Then what is the gray code of this? 0100. Then what is the gray code of 0100? This is XOR operation. This is XOR operation. I hope you are all aware of what is meant by XOR operation. If you're not aware of what is meant by XOR operation, no worries. We will discuss when we are discussing about combination logic. Okay. Yeah. So let's see. It is 0 and 0 XOR 1 is nothing but 1, and 1 XOR 0 is nothing but 1, and 0 XOR with 0 is nothing but 0. So 0110 is our answer. Everyone agree with me? Yes. Now, gray to binary conversion. So here we have zigzag manner. So if this is our gray code, then this is how we are going to convert it into binary. So we will follow a zigzag manner. So the first digit will be simply written, and from the second digit, the first digit result and the second digit will be XORed, and the resultant will be given like this. Let's take the previous example only. 0110. 0110. So what will be our binary code? 0 double. Sir, we can. We are only using XOR. Can we use other gates? No. Gray code conversion is achieved by XOR operation only, right? I don't know other methods like how to convert the binary to gray code. Yeah, significance, everything we will discuss. Please wait. Okay, we are going step by step. Yeah. So all of you got the particular answer? Yes. Now, so your task is, okay, this is enough. From 0 to 10, write down the gray codes from 0 to 10. Okay. First write the binary code and the Greek code from 0 to 10. Okay. Then you can only see the difference. Okay. Instead of me writing everything, you try this, you take it as an assignment. You write the binary codes from 0 to 10 and write the gray codes from 0 to 10. Okay. Then according to your answers, I'm going to explain what is the significance, what are the applications, everything. From your answers only, I'm going to take the conclusions. Okay. Yes. Yes. Okay. Yeah. So that's all for this session. So we have completed the basic codes, gray code and BCD codes, Axis 3 code. Okay. So the applications of this particular gray code, we have seen in the definitions also, right? Unit distance code, everything we are going to discuss from the answers which have given. Okay. So just please try, and in the next session, anyone please share your answer with me. Then I will discuss from your answer. Okay. Yeah. Okay then. So if you are having any doubts or queries, you can stay and ask me, or else we can end the session. I hope your first assignment we have just simply yeah, application of this K map. What I'm telling, why we are using in K map, because it is a unit distance code. Okay, it is a unit distance code. Why it is a unit distance code and what is meant by unit distance code will be explained from your answer which you have given. Okay, so I've given one assignment, right? So please write the gray code and binary code. Okay, and yeah, in 1 minute, and from that I will explain this particular answer. Yeah, 1 minute, and please wait for the attendance also. I will post the attendance sheet. 1 minute. Thank you for reminding me. 1 minute. I'm not seeing your messages. Please don't type now. One minute. Please wait for a minute.